Hey, well, I'm starting to write my notes this time. I think this video is just meant to be because I already did this video and it went horribly wrong on every level. I was very confident as I just made up calculus. So one, not good. And then two, my audio had mad feedback, like it was almost impossible to hear. And I was still going to make you do it because I didn't want to redo it. And then I think Fates just intervened and were like, no, you just made stuff up, so you got to redo it. I hope the audio is better. My headphones in, so it's not so echoey. So I hope you can hear it clearly. And if not, I'll learn along with you. So this is objective 1.8.1, where I'm trying to preview the squeeze theorem. My goals in this video is just to give you an intro to what the squeeze theorem is and try to demystify it. It's a pretty logical theorem, and it has a very tough proof, which you will see in 2 videos from now. So I wanted to preview, and I said warn to scare you, but I'm not here to warn you. I'm just here to prepare you. So there's no frowns. Look at that. I give a little smirk. No, he's more eager, more excited. Looks a little angry, actually. I'll fix the eyes later on. But that's my goal, is to give you a little preview so you feel a little more comfortable with it. And then know that when that video comes up, that really tough calculus proof, don't shy away. You all can do it. It's just some tougher calculus language, but I have confidence that you all can understand the rationale of where the squeeze theorem comes from. One key point, it's also called the pinching or the sandwich theorem, which makes sense in a sandwich sense. If I have a sandwich and I'm squeezing something in between, that's the idea of the squeeze theorem. I was going to draw a sandwich, but I think you get the idea. I think a fair point is why. Why do we bother with the squeeze theorem? And it is your last resort of last resorts. So you remember the Khan Academy flowchart, I hope you do, where our first option was we always want to plug in the hopes that the limit is continuous and that it operates like function notation. When we plugged in, we learned, is there a vertical asymptote there? Did we find the limit? Or did we get indeterminate form, which means we now need to try to rationalize, we need to try to factor, or we need to do some trig identity substitutions. The very last resort on that was make a table of values to see if you can find where the limit is. This is even the last resort beyond that, where it's like, if I have no other options to find the limit, we can at times use the squeeze theorem if we hit 2 really important criteria. And here are those 2 criteria. So criteria number 1, the target function, which the target function means the function that's being squeezed, like pushed toward a certain limit, which in this case, in the picture up here, is g of x. It's a little bit for you all. It must be between the other 2 functions. And I've called them, I think they are called, the other 2 like squeezing functions. So in this case, that's f of x and h of x would be considered the other 2 functions that are squeezing, that are pushing g of x toward a certain limit. And what we're really trying to figure out is, I'll give one example. This does not match this picture. I'll show you in a second. We're going to use the squeeze theorem in this video to find this limit. The limit as x approaches 0 of x squared times sine of the quantity 1 over x, which we will be able to figure out in a second. But to show you more mathematically, what it means is that the target function must be between the other functions. It's this idea that h of x, which is referring to y values. Recall that g of x, f of x, h of x all refer to the output values of functions. So it's saying that h of x's y values have to be less than or equal to all of the y values for g of x, which in turn have to be less than all the y values of f of x. If this is true, then we've met the first criteria of squeeze theorem, and we might be able to apply it if the second criteria is also true. The second criteria is saying the limits of these squeezing functions have to be the same at the value in question. If they are the same at the value in question, if these squeezing outside functions are pushing the middle function toward an exact value, again, at the limit in question, then sweet. We've met the criteria of squeeze theorem. We can apply it and make a conclusion about the limit of this function that otherwise we couldn't find. But mathematically, we're saying the limits as x approaches c, c representing just any value or the target value. In this example, we're messing with as x approaches 0. So that would be x approaches 0 for this limit. The limit as x approaches a certain value of the function f of x equals L. I'll say if the limit as x approaches a certain value of f of x, and if the limit as x approaches that same value of the function h of x also equals L. So if both of these squeezing functions approach the exact same limit, and we already concluded that this is true, we can actually go ahead and jump to conclusion now. If we've met these two criteria, we can then conclude then the limit as x approaches c of the target function g of x equals that same limit value that these squeezing functions approached. So now let's give an example of how we can use the squeeze theorem to find this limit that otherwise we really wouldn't have any options to approach. Now this is where I messed up. I first found this limit in the other video, and that's hilarious because this limit does not exist. I'll show you what I mean really quickly because I think it's cool. So I'm going to take this away. But I found this limit. I'll just call it a of x is equal to the sine of the quantity 1 divided by x. This is actually showing off a pretty classic oscillating discontinuity, and I should have known there's no limit there because by the nature of it being called a discontinuity, it's been a long day. But what's interesting is even though this itself does not have a limit as x approaches 0, this, the g of x function we're about to find the limit for, does. And it starts with this truth about sine functions. Notice even in this oscillating discontinuity, the largest y value is positive 1, and the smallest y value is negative 1. If I just type in a bunch of random sine functions, like sine of 5x, notice I have more periods now, like the sine wave's going quicker, I guess you could say, which is not true. But the biggest y value is 1, and the smallest y value is still negative 1. And you can do this, I can call this x squared. No matter what I input, the largest y is still 1, the smallest y is still negative 1. The only time that changes is if we actually give a coefficient to the sine functions or trig functions, then the amplitude changes. But we can't input a value that's going to make sine go outside the y range of negative 1 to 1, which is really interesting. And so we're going to start with that knowledge to apply the squeeze theorem here. So knowing that idea, that if I had just sine of the quantity 1 over x, I know for a fact that no matter what the input value is, that is always going to be between the y values of negative 1 and 1. And so my goal is to find this limit right here where I can very cleverly say, all right, what if I multiply every part of this compound inequality by x squared? I'm essentially distributing that value to all 3 parts of the compound inequality. And if I do that, I haven't changed the balance of the inequality. And so now I'm arguing that negative x squared is less than or equal to x squared times sine of the quantity 1 over x is less than or equal to x squared. Well, what's cool is we're now actually evaluating the limit we care about, which is x squared times sine of 1 over x. So now I have to hit the 2 criteria. I have to, 1, see, do these outside functions, negative x squared and x squared, do they approach the same limit? And are we confident that all of these y values are always less than, and then in turn bigger than this function? And if that's true, then we can actually apply squeeze theorem. So 1, I'll do it right here. It's a really bad sketch. If I sketch x squared, that's just a quadratic equation. That's your standard form of a quadratic. So x-intercept, y-intercept right at the origin, and then negative x squared would be the same thing, just facing down. So that's really interesting because we know that the limit, I can write it right here, the limit as x approaches 0 of the function negative x squared equals 0. Quadratics are continuous functions. They have no discontinuity, so we can just plug in to find the limit. We also know that the limit as we approach 0 of x squared equals 0. So far I've checked criteria too that, yep, they approach the same limits, but I have to make sure that the y values of negative x squared is always less than these y values, and the y values of x squared are always greater. Now, there's no great way to test that. I could just plug in values as they approach 0. If I was going to do it with a table, I'd plug in -1, -0.5, -0.1, -0.001 to see, are these y values always bigger and then in turn less than that. But to save some time, I can show this, which is really cool. Let's go back to our original function. Here's where we're trying to prove that it does have a limit. And so if I now turn on x squared and negative x squared, check this out. If I zoom in, I zoom out one, notice how the x squared function for all the y values is always bigger than all of the y values of the blue function, which is x squared times the sine of 1 over x. And then negative x squared, its y values are smaller than every single y value for our blue target function on forever. And so what's really cool is we just met both criteria of the squeeze theorem. So now let me share my screen again. And so because we proved that this is true, we proved that these y values are always less than this function's y values, which are always less than this function's y values, we can now conclude, there's a better way to phrase this justification-wise, but I'm just gonna go ahead and include the limit as x approaches 0 of x squared times sine of 1 over x is also equal to 0 because negative x squared, the y value is always less than that, these y values are always less than these y values, and both of these functions approach the exact same limit. So as you saw in the picture, x squared times sine of 1 over x is literally being pushed toward, it's being squeezed toward the limit of 0 as x approaches 0 because both of these squeezing functions pushes it to that value. I hope you could hear me clearly. I really do. I don't want to do this a third time. And as always, ask questions if anything's on your mind.